Let's start the exercises next, and this is the second one. Here you see a new function, mangold function, denoted by capital lambda, and this is the definition. It's a number theoretic function. That means n is the positive integer and lambda of n is defined to be equal to log p if n is equal to p to the power k, where p is the prime and the exponent k is some positive integer. Otherwise, it's defined to be equal to 0. In all other cases, lambda of n is 0. And we have to prove these facts about this function. For any positive integer n, lambda of n equals summation mu of n divided by d times log d, where d varies over all the positive divisors of n. And that is also equal to minus summation mu of d log d. This time we do not have n divided by d, and again d varies over all the positive divisors of n. So let's now prove these things. We start the solution with something whose relation to this solution may not be apparent immediately, but it will be clear soon. So let's see what we are doing here. We have taken any two positive integers m and n which are relatively prime. And then what we do, we consider this sum, the sum of the lambda values of all positive divisors d of the number mn, the product of m and n. And by the lemma before theorem 6.4, this lemma actually has no number assigned to it, so it's just a lemma which appears before theorem 6.4. This sum can be written like this. Actually, it is that result which tells us about the positive divisors of this product mn, where m and n are positive integers and they are relatively prime. Any such positive divisor is of the form d1, d2, where d1 is a positive divisor of m, d2 is a positive divisor of n, and they are relatively prime. Well, that automatically follows from this. Okay. So it is that result, and that's how I have written it like this, where d1 varies over the positive divisors of n, d2 varies over the positive divisors of n, and GCD of d1 and d2 is equal to 1. Alright, so now you see that here we have lambda of d1, d2. Now we are going to look at some cases. Some cases means actually two cases. In one case, these lambda values will be 0. In another case, they will not be 0. So that will help us reduce this sum to something that can be managed easily. Let's see. Now, depending on what the numbers m and n are, there may be many positive divisors of m, many positive divisors of n, many different types of d1 and d2. Let us look at the case where d1 and d2 are both greater than 1. Because both of them are greater than 1 by the fundamental theorem of arithmetic, both are divisible by some primes, at least one prime. And those primes are distinct primes because they are relatively prime. d1 and d2 are relatively prime, so the same prime cannot divide both of them. And that is why in the product d1, d2, those primes will appear which are distinct, and the consequence is that d1, d2 cannot itself be a power of some prime, some single prime. But then by the definition of our lambda, lambda of d1, d2 is equal to 0. Now what is the consequence of this? The consequence is that in this sum, all those d1, d2s, both of which are greater than 1, for all of them, the corresponding lambda term is 0. So this drastically reduces the complexity of this sum. Now what does that mean? It means that we do not have to consider those terms which correspond to d1, d2, where both d1 and d2 are greater than 1. That means we just have to consider those terms where either d1 is equal to 1 or d2 is equal to 1 or both of them are 1. However, that single case where both of them are 1, d1, d2 is just 1. And if you go back to the definition of lambda, lambda of 1 is equal to 0. So that can also be neglected. That means this sum will now reduce to two sums. In one of them, d1 is equal to 1 and in the other, d2 is equal to 1. And from there, then we can say something. So this sum reduces to these two sums. But let's look carefully at these two sums and try to understand what went on here. We cannot just simply carelessly say that, okay, we get these two sums and that's it. So this sum is the result of considering that case where in all these things, d1, d2, d2 is equal to 1. Okay. So that means here d2 will vanish, so you have d1. Here d2 vanishes, you have d1. But why did I not write mn here? Why am I writing m? That is because d1 varies over all the positive divisors of m. So ultimately, if I write mn here, whatever sum I am going to get, I will get that same sum if I write m here. Because ultimately we are just talking about d1 and d1 is varying over the set of all positive divisors of m. That is why. Similarly, that other case where d1 is 1, you get this sum. Okay, and we are not immediately going to do anything with this. We let it sit like this. We are going to use it to do something else, which is in fact our main thing now. Now next we are going to make a claim and then we will prove that claim, and from that claim those things which ultimately we have to show, they will come out as consequence. Now this is our claim. We claim that the sum of all the lambda values of the positive divisors d of n is equal to log n for all positive integers n. And we will now prove this claim by induction. And in carrying out the induction step, we are going to need this. That is why I did that. So we apply induction on n to prove this. And the basis is very easy. So we consider the base case which corresponds to n equal to 1. We consider this sum where now you have 1. What are the positive divisors of 1? Only 1. So that means this sum in this case is just lambda of 1. Because 1 is a positive integer which is, well, it is actually a prime power, p to the power 0 for any prime, but that exponent is 0. It's not a positive integer itself. That is why by definition lambda of 1 is equal to 0, which is also log 1. Log 1 is also 0. So in this case at least our claim is true. And next we make the induction hypothesis, which is this. Suppose that the claim is true for all positive integers k less than or equal to n. That means for all such k, the sum of the lambda values of all the positive divisors of k equals log k, where n itself is some arbitrary but fixed positive integer. That means we are applying the strong version of induction. And now we have to prove the claim for n plus 1. Now we go for the induction step, and here also there is an easy case which we can first consider, in which n plus 1 is a prime. If it is a prime, then what will happen to this sum? What are the positive divisors of a prime number? The prime number itself and 1. So you get lambda of 1 plus lambda of n plus 1. Lambda of 1 is 0, so that vanishes. And what is lambda of n plus 1? Note that now n plus 1 is a prime, so it is in particular a prime power also, where the exponent is 1. The exponent is positive here, and that is why by definition lambda of n plus 1 is log n plus 1. So we see that we are in fact getting what we want in this case. And now next we have to consider the case where n plus 1 is composite. So next we consider the case where n plus 1 is a composite number. Now here also actually there are two cases. One of them is this. Let there exist positive integers alpha and beta such that both alpha and beta lie strictly between 1 and n plus 1. Both of them are greater than 1 and less than n plus 1. And their product is n plus 1. In fact, this equation with these inequalities tell us that n plus 1 is composite. Fine. But here you see one extra condition, that GCD of alpha and beta is 1, that is they are relatively prime. Now if you think of this entire thing for a while, let's just think of an example. Say n plus 1 is 12. Okay. Now what is the prime factorization of 12? 2 square times 3, 4 times 3 is 12. So as alpha you can take 4 and as beta you can take 3. So actually when are we having this case? We are having this case for those numbers where the prime factorizations have at least 2 distinct primes. Otherwise you won't have this condition. For example, if you take the number 4 itself, right? For the number 4, will you find such alpha and beta? See, alpha and beta both have to be greater than 1 and less than 4. So there is only one possibility, that both of them have to be equal to 2. But 2 and 2 are not relatively prime. So the cases where the number n plus 1 is composite but a prime power, they are not these cases. These cases means this case. They are different. We have to handle that also separately. This case, however, includes those numbers like 12. Now what can you do about this case? Let's see. So in this case also, of course, we consider that sum where now we have n plus 1 in place of n. And n plus 1 is alpha beta. And this is precisely that case with which we started our solution. So we can use that result here. Note that alpha and beta are positive integers which are relatively prime. So this sum reduces to these two sums, the sum of these two sums, where you understand that here d1 varies over all the positive divisors of alpha and d2 varies over all the positive divisors of beta. I have deliberately used d1 and d2 here so that you can go back and see the thing that we are using. But what about the numbers alpha and beta? Alpha and beta are both less than n plus 1 and they are positive integers. And that is why, by our induction hypothesis, this sum is equal to log alpha and this sum is equal to log beta. Now I think you can see almost immediately where we are going with this. So log alpha plus log beta is logarithm of alpha beta, but alpha beta is n plus 1. So that's how we see that in this case also our claim is true. So that leaves us with that one case where n plus 1 is a prime power. So next we consider that case where n plus 1 is p to the power k, where p is the prime and k is the positive integer at least 2. We are not considering the value k equal to 1 because otherwise n plus 1 will be a prime, which we have already considered before. And we straight away start with this sum. Summation of all the lambda values of the positive divisors of n plus 1. And n plus 1 now is p to the power k. Now the positive divisors of p to the power k are very easy. 1 p square all the way up to p to the power k. So this is the sum. Lambda of 1 is 0. But these are all prime powers where the exponent is a positive integer. So by the definition of lambda, these are all log p. How many log p's? 1 log p, 2 log p's, like that it goes. So obviously there will be k log p's or k times log p. But we know this property of logarithms that when you have k log p, that k goes inside and becomes exponent of p. So log p to the power k, but p to the power k is n plus 1. So again you are getting log n plus 1. So in this remaining case also our claim has been proven to be true. And that is why this completes the induction and establishes our claim. I have written what we have proved just now once more, because from here we are going to next have what we ultimately want to have. But using what? Using Mobius inversion formula, and that is why we have been doing all these things. So we next apply the Mobius inversion formula to this equation. So the places will get swapped, lambda will come outside, log will go inside, and there will be mu also. So lambda comes outside means we have lambda of n, that is equal to summation, log goes inside and has d. But mu also is present with the argument n divided by d, input n divided by d. And d as usual varies over all the positive divisors of n. But recall that it has two versions. Two versions means in theorem 6, in fact this is our Mobius inversion formula, there were two things in the conclusion. That this sum is also equal to this sum, where you can switch the places of d and n divided by d. You can keep d with mu and you can slide this n over d to log. And now this is going to give us that other claim that we have in the exercise. One of the claims is this itself, but now we have to work with this and get the other claim. There are a few lines. Now next what we do, in place of log n divided by d, we write log n minus log d, one of the properties of the logarithm function. And then of course, you just multiply, so you get log n times mu of d minus mu of d times log d. And then the sum becomes two sums, difference of two sums, this. And in the first sum, log n goes outside of the summation because it is not changing as d is changing. With respect to d, log n is constant. So it is present in every term, so you take it outside as a common term. And you are left with summation mu of d as d varies over all the positive divisors of n minus, this one just stays like that, summation mu of d times log d as d divides n. Now you go to the text and see the statement of theorem 6.6, which tells us something about this sum. When we were studying the function mu, at one point we considered this and we found that this sum is equal to 1 when n is 1, but if n is greater than 1, then this sum is 0. And the nice thing about this entire term is that when n is equal to 1, this is 1 but this is 0 because log 1 is 0. Whereas when n is greater than 1, this is non-zero but this is 0. That's why this part anyway vanishes and we are left with just this. And that's what we had to prove.